Good afternoon, everyone, and welcome to this session on streaming analytics and how the BBC's built an enterprise-scale application to deliver real-time audience insights. My name is Hin Yi, and I'm a prototyping engagement manager at AWS. This session will be an in-depth guide into streaming analytics and the AWS services that you can use to build a highly scalable streaming architecture. We'll discuss how the BBC built out this functionality, and we'll cover key considerations for your own streaming data initiatives, including common patterns for data enrichment and the trade-offs between latency and throughput. But first of all, why are we here? Streaming data has become an enabler for organizations to achieve more and really make the most out of the massive amount of data in their hands. The BBC is used by nearly 9 in 10 adults in the UK, with 3/4 of them using BBC News on a weekly basis. Across all of its services, this translates to upwards of 5 billion analytics events generated daily. And this number is only set to grow in the coming months and years. To unlock the value of this data, we need to be able to act on it as soon as it is produced. And that is in real time, instead of waiting for hours, days, or even weeks to extract valuable insights. The value of recency in data cannot be overstated, as it enables organizations to achieve more and really make the most out of the data. It also allows them to respond quickly to changing market and user requirements. Insights from data are perishable and can lose value quickly. As we're waiting on batch processing jobs to complete, we're missing out on the full value of the data, especially when we want to move from reactive to proactive decision-making. Streaming data can provide you with timely and actionable insights and allow you to react to your customers and the market at high speed. And today, we see customers using streaming data for an unlimited number of use cases. For the BBC, real-time analytics has enabled their internal teams to respond more quickly to their users and serve up personalized content at the right time. For instance, they can be given relevant content on other BBC services while watching a live event on BBC iPlayer. Now, let's say that you are a media and entertainment company, and you produce on-demand content including TV shows, documentaries, and movies. And you have a wealth of data, including user interaction data, content metadata, and viewing patterns. And you want to be able to leverage that data to improve your insights and, more importantly, enhance the user experience on your platform. First, you'll want to ingest your data efficiently, and there are a few options for this. You can use Amazon Kinesis data streams to continuously capture and store terabytes of data per hour from hundreds of thousands of different data sources, including connected devices, applications, and websites. You can also use Amazon Managed Streaming for Apache Kafka, also known as Amazon MSK. Kafka is a popular open-source event streaming framework that is best suited for building real-time data pipelines and streaming applications. You can use it to process and analyze your user interaction data, like video playbacks, and you can also set up Kafka topics to trigger actions based on user events. Now, let's say that you want to load your user interaction data into downstream stores, such as a data lake or analytics tools. But you first want to enrich it with other data sources, including your users' demographic information or their geolocation. You can use Amazon Data Firehose to capture, transform, and load your data into these data stores. And it also provides built-in transformation capabilities, including filtering and masking of sensitive information. Finally, if you want to run more complex event processing, including stream-based machine learning to detect anomalies in your user activities, you can use Amazon Managed Service for Apache Flink. Apache Flink is another popular open source framework that's designed to run stateful streaming applications at any scale. By leveraging these AWS services, you can now build a more resilient and scalable data architecture that suits your growing needs. And most importantly, enhance your users' experience on your platform. Now, how do we use these services in real life to build an end-to-end streaming data pipeline? To put this into action, the BBC started their journey by partnering with our AWS prototyping team to build the foundations of a highly resilient and scalable data streaming ingestion pipeline. We'll now dive deeper into the technical decisions behind the architecture and how the BBC evolved it to suit their growing needs. And we'll also review best practices that you can directly apply to your own streaming data initiatives. Now, to help us bring this to life, I'd now like to invite John from the BBC team.
Good afternoon, everyone. My name is John Ewing, and I'm a senior architect at the BBC. My areas of interest are around audience analytics, stream processing, and machine learning. Today, I would like to take you through the journey the BBC has gone on to improve our understanding of our audience. The BBC's mission is to inform, educate, and entertain. But more importantly, we need to inform, educate, and entertain everyone within that audience. And this is not a new challenge. So pictured on the screen is one of the first audience analytics devices that we used. So in case you're wondering how that works, in the days of 4 television channels, whenever there was a major television event, the national grid would experience huge power surges. For instance, at the end of the 1990 World Cup semi-final penalty shootout between England and West Germany, there was a 3 megawatt surge when the shootout finished. And this was caused by 1.1 million kettles being put on so that everyone could have a cup of tea. And from that 1.1 million figure, you're able to extrapolate that 26 million people were watching that event. However, as 4 channels became 5 and then into the Freeview era where there was hundreds of channels, that method was no longer as effective. And so how we evolved that was there are volunteer households who have a special set-top box that would tell you what programs they have been consuming, and then from that you can extrapolate to the whole audience. But even that is becoming ineffective. People are no longer consuming solely linear television. Consumption of media is moving to streaming and catch-up services. So in order for us to continue truly understanding our audience, we need to have a digital-first strategy in order to address that. And the challenge is not just about television anymore. The BBC provide a wide range of services. We have iPlayer, sounds, sport, news, weather, and even Bitesize, our learning platform. And beyond that again, the scale of our audience really makes this a challenge. 11 million viewers watched the coverage of the Eurovision Song Contest final. 21.2 million people watched the coverage of the Women's World Cup final. And there was more than 45 million page views on the day that Queen Elizabeth II passed. So, what was the starting point for our journey to try and understand the audience? So, at the heart of it is a BBC SDK. We have produced this so that we can abstract away the challenge of doing analytics from our developers so they can concentrate on producing features for our audience. So if you read an article on the BBC News website, for instance, we emit an event with the ID of that article, it goes to a third-party analytics provider, and they provide some enrichment. For instance, they take the user agent string and work out what type of device you were using. When that is complete, that data gets rolled up and dropped into our data lake in Parquet. And that is pretty effective for answering certain types of questions, such as like, what were the overnight viewers for certain programs. However, if I go back to Hinyi's slide, we're missing out on a lot of opportunities. There are many reactive use cases that we cannot do with that 40-minute latency. A prime example of that is being able to provide recommendations to viewers when they've finished watching something in iPlayer. 40 minutes is not going to cut it for that. So in order to unlock that first use case, what we did is we added a second path into the SDK. This directly sends to our own data platform. And what we did is we stood up a Java API endpoint running in EC2 that collates the events sent to it and writes them into Kafka. And then on the other side of Kafka, we have several consumers, again, bespoke Java services, which consume these events and forward them on to other services, such as the recommendation engine. So we did that, and that worked really well for us. But there were a few issues again. So in the web service, whenever we want to add a new event type, we have to actually do development work and then redeploy the service. And then similarly for the downstream consumers, because they are all implemented in a bespoke fashion, if we change our event schema or want to add new schemas, we have to duplicate effort in them, and because they are not identical, that work is usually double the work. So at this point, we paused and thought we need to really rethink our approach to this, because we want to scale to hundreds of events and potentially hundreds of consumers. And so we partnered with AWS to try and work out what would be a scalable, reliable architecture for this. And really, when you embark on a large project, it's important to understand the why of why you're doing this project. One of the prime drivers was owning our first-party data. And what I mean by that is, in the old system, we have the data modeled in quite a generic way to work with the third party. But what we really need to be able to do is model the data in a BBC way. We also, like I say, want to unlock new use cases to deliver audience features, and we can't do that with the 40-minute latency. And the other thing we wanted to do was increase the consistency of tooling among teams. We were spending too much time developing bespoke ways of consuming these events in real time and forwarding them on. And so when we evolved the prototype, the things we targeted in the first version were being able to easily add new events, avoiding the duplication, and being able to measure the completeness of our data. By completeness, what I mean is, for every event that the API endpoint receives, we can prove that all of those events made it into the sinks, such as S3 or our data warehouse. And so in order to really drive that forward, we were going to need some new technology in order to deliver these features. The first aspect we wanted to look at was around removing the effort to add new event types to our platform. So we looked for a schema format. A schema format is a way of representing the structure of your data in a language-agnostic way. We considered Avro and Protobuf for this, but we finally settled on JSON schemas. Our thinking behind this was that it has wide language support, including for all of the languages that we develop in at the BBC. We use JSON frequently in our APIs so that it is easy to retrofit without having to do serious rewrites on existing services. And it has good support for a lot of the tooling we were hoping to use. The Glue Schema Registry, MSK and MSK Connect all have native support in Amazon for JSON schemas. And then the second part that we wanted to try and use technology to address was this reinventing the wheel. Every time someone wanted to consume real-time events out of the stream, we did not want people having to solve the same problem over and over again, but in subtly different ways. And so for that, we looked for a streaming framework. Again, there are quite a few candidates, and most of them will be valid, such as Kafka Streams or Samza. But in this case, we picked Apache Flink. It has really good industry support. There are a lot of large internet economy companies which use Apache Flink at scale. It has a really good framework for working with time, which I will talk about in a minute. and there's a managed version available in AWS. And that last aspect was important to us because it let us concentrate on delivering the features we were trying to for our users and not standing up an execution environment to run an open source framework in. And so if I put together all of the things I've described there, we still have the BBC SDK at the heart of things, sending the events. However, now in our Java web service, we're using the JSON schemas. And one of the powerful things that gives us that if data comes in, which does not match the schema or is malformed, we can now automatically dead letter queue that data and save it for inspection later. But it does not go into our lake and pollute the data. And then to serve the use case of being able to show the top read news articles, we developed an Apache Flink application to consume the stream, calculate those aggregates, and then write them into InfluxDB time series database, and then present the results to the journalists via Grafana. And because we were adding these new events that were modeled well now in JSON schemas, we wanted to preserve them directly into the lake. And because, as part of this project, we used the Glue schema registry to store the schemas, it made it very easy to stand up MSK Connect to automatically pick up the schemas, consume them, and write the data in Parquet format into S3. Subin will talk a bit more later about the Glue schema registry. And because of the use of schemas in a schema registry, schema evolution and adding new event types is very low maintenance. All of the components, such as the API endpoint, the Flink consumers, and the MSK Connect syncs, can subscribe to the schemas from the registry and automatically pick up the new versions. So that all sounds great in practice. However, like any real project, this did not work first time. And so I'd like to share with you some of the lessons we learned from trying to roll this out at scale. The first lesson that we learned is that time is annoying. When we're calculating the top read articles in order to show them to journalists, we do use a very common pattern. We use a window function. So all that a window is, it is a time period that as the streaming events come in, you place the events into it. So what should happen is that as we look at the events time as they come in, we place them into a window based on that time. And then when an event occurs that is past the end of the window is closed, we calculate the top read article, and then we flush that into the sink. So that seems simple. That should be really straightforward. So what we actually saw was events would come in, be correctly placed in the window. But what we would then see is we would get an event from far in the future. And the effect of that is it would prematurely not only close that window, but lots of subsequent windows. And then valid events would come in and be rejected as late arriving data. So our results from the service were completely wrong. The reason for that is that we were trusting a client-side timestamp. And what we found is the client-side timestamps have wild variation from years in the past to years in the future. And so we resolved this by changing to the received timestamp provided by Kafka. And that allowed us to compute accurate top story statistics. And that experience also made us really look into our data quality, because it's not just the timestamps that were issue. We would find things like completely malformed timestamps that were unparsable. We also saw inconsistent representations of data. So depending on the implementation platform, i.e. Android, iOS, web, you would see Booleans being represented as 1 or 0, true or false, or indeed something else. And so that made our data sets very hard to work with for downstream consumers. And in some cases, we even found malicious messages. People were inserting content into fields that was designed to do SQL injection, shell escapes, and things like that. But fortunately, because we've been using JSON schemas, we're able to tighten up our schema definition, and the vast majority of these messages now get rejected into the dead letter queue. And because we're a 24/7 news organization, we get quite a lot of variance in our traffic. So at the start of the day on this graph, you can see people waking up and beginning to log on and use the BBC News website. However, what you can also see is we get large cliff faces of traffic. This is caused by breaking news stories. So when something significant happens, BBC News app users will get a push notification. And that causes people to go on, log on, read the story all at the same time. And that was challenging for us when we initially tried using the default auto-scaling based on CPU metrics, we found we would lag quite far behind because it just wasn't aggressive enough to deal with absolute cliff face walls of traffic. In the interim, we have mitigated it by scaling out more to find a sweet spot between being overscaled and lagging too much. And a bit of future work we're doing is to look at using custom metrics so that we can more aggressively scale out or even preempt the breaking news story. The final thing that I would like to talk to you about is data skew. So when you have a stream, the stream is divided up into partitions, and each partition is consumed by a Flink task. And the default behavior is to use a random distribution so that as messages come in, they're arbitrarily assigned and an equal amount of traffic goes into each partition. But there are some use cases where that isn't effective. For instance, if you were to try and answer the question, how many unique readers were there for this news article in this time period, then if you use a random distribution, the memory requirements for doing it that way are very high. So the obvious next step is to partition by something such as the article ID. And so this time when you see these partitions, instead of just randomly assigning the messages, you assign them based on the ID of the article people are reading. But it's important to understand the behavior of your audience. When we have events such as the draw for the Champions League group stages, what we see is something like this. We have all of the audience reading the same article, and they often hit refresh a lot to try and see who their team drew in the group stages. And so that skew causes quite a few problems. The performance of that single task becomes a limiting factor of your job. And even scaling the job out is not going to solve that because the distribution is so skewed. Fortunately, if you can accept about 1% of inaccuracy, there is a way of working around this. You go back to using the random distribution and you use statistical methods such as the hyperloglog method, which can give you accurate cardinality estimations in a fixed amount of memory. So in that way, you get the best of both worlds. You get the even distribution of your load, and you also are able to calculate the cardinality without using huge amounts of memory. So to sum all that up, at the BBC, by utilizing open source schema formats and streaming frameworks, we have been able to unlock new use cases to deliver value for our audiences, reduce the time to deliver new events, and reduce the maintenance burden on our teams. I hope this journey has been interesting for you. If you're interested in using stream processing for your own use cases, Subham is going to describe some of the considerations you should take into account.
Thank you, John. It was really interesting to know how BBC has built a scalable real-time data platform and the lessons learned throughout the journey. Now, I'm sure many of you are in a similar journey or you are going to be. My name is Shubham Rakshid, and I'm a streaming specialist solution architect in AWS. And today, I'm going to talk about some of the key considerations that you should consider while building a streaming data pipeline. Well, John has covered some of the important aspects about late data handling, spiky traffic, and data skew. I'm going to add a few more on top of that. It starts with capacity planning, and it depends what type of services you are using and the flavor of the services. AWS provides two different streaming storage, Kinesis Data Stream and Amazon MSK. In Kinesis Data Stream, we offer provision capacity mode and on-demand capacity mode. In the provision capacity mode, you have to define the number of shards required for your workload, and in the on-demand capacity mode, the service auto-scales the number of shards. Similarly, in Amazon MSK, you are in charge of defining the number of brokers that is required for your cluster if you go for a provision mode. And in the serverless mode, the service auto-scales depending on your workload. Now let's look into the latency throughput trade-off. Latency is referred to as the amount of time it takes to move the data from source to destination. And throughput refers to as the amount of data that is moved from source to destination. Let's look into an analogy to better understand the trade-off. Imagine a group of friends need to go from point A to point B. They can take a car, start at their own time, and reach the destination. If there is no traffic, each and every one will have a lowest latency in reaching the destination. However, there could be other cars on the road, so there is a chance of traffic. And if there is traffic, there will be queuing. And all the successive cars caught in traffic will have higher time in reaching the destination. Let's look into this, that how this analogy refers to streaming storage like Kafka. Well, the car referred to as the individual produce requests sent to Kafka topic. And the traffic is caused due to higher number of produce requests and also the limitation of number of maximum in-flight requests. Think of it, it's like lanes in the highway. If you have a 2-lane highway versus a 6-lane highway. And also, Kafka also gives back acknowledgement once they receive the record, so it depends how long the Kafka is taking time to process those records. As more and more requests are sent, well, it increases the latency because it takes more time to get back the acknowledgement, and it also negatively impacts the throughput. However, they could do something else. They could gather at a bus stop, all board in the same bus, and they could actually move from point A to point B from that bus. Well, some have to wait longer in the bus stop, or somehow will probably catch the bus the very last moment, but all of them will reach the destination at the same time. Now, in this scenario, there is a chance of less traffic, or it will be much lesser traffic compared to the previous one, because there's less vehicles on the road, and each vehicle is carrying more passengers. Now, vehicles carrying passengers, what does it refer? Somehow as a batching. Well, I'm not talking about traditional batching here, because I know that traditional batching will actually increase the latency and is not fit for streaming use case. I am talking about micro batching. It is important to find out your optimal batch size that actually serves your throughput and also reduces the latency. So you have to know those latency and throughput SLA for your workload and have to work backwards from there. Let's look into how this analogy again relates to Kafka. Well, in this scenario, the bus refers to as the micro batch produce request. And there is less amount of traffic because there are fewer requests sent to Kafka. And throughput is improved because of micro batching, and each of this batch is getting bigger and has got more records packed in. And the interesting thing about latency is the latency of this micro batch is lower than some of the individual records of the batch itself. So this is the latency throughput trade-off you have to consider while building your streaming pipeline. Moving on to processing and delivery guarantees. Well, the delivery refers to how strongly your streaming pipeline enforces delivery of data from a source to destination. And processing refers to as the processing guarantee you can get while moving the data from source to destination. Now, while building a streaming pipeline, you may be interested to end-to-end guarantees. And for that, it is important to consider it is a responsibility of all the components coming together, including the source and destination. Now, in a distributed messaging system, like Kafka or Kinesis data streams, mostly in Kafka, I would say that computers can always fail independently of each other. Now, how exactly your broker can crash or there can be some kind of network failures can happen. Now, how your producers behave in this scenario will actually ensure what kind of delivery semantics you are getting. Kafka supports multiple different acknowledgement modes. The strongest durability is obtained when the data is written to the leader partition and replicated to other brokers. And once the data is obtained by Kafka, it will give back an acknowledgement saying that, hey, I have got the data. But however, there may be scenarios you may not actually receive the acknowledgement because of any acknowledgement timeout or any kind of errors. Now, how your producer reacts to the scenario will define what kind of semantics, particularly delivery semantics, you can get out of Kafka. In an at most one scenario, the producer does not retry if it gets an acknowledgement, timeout error, or any other failure. And in at least one semantic, the producer retries if it actually gets an acknowledgement, timeout error. As you can see, in at most one scenario, while you can have a data loss because you are not retrying, but you will not have any duplicates. However, in at least one semantics, you may end up having duplicates, but there would be no data loss. And in exactly one semantics, even if the data packets are retried because of any failure scenario, your data is only sent to Kafka exactly once. However, if you are building an end-to-end pipeline, you would probably be more interested into end-to-end exactly once. And this is achieved under a very specific condition, and it can be expensive in terms of resources, throughput, and latency. And it's important to consider that your source is able to deliver the data to the message broker exactly once. Your message broker can receive the data. Your consumer application process the data exactly once and write it to the destination sink exactly once. That means your sink should be able to handle, it should be an idempotent sink or a transactional sink. Next, we move on to ordering guarantees. So ordering is referred to as that data is always referred to in the same order it is written in the first original time, actually. So in Kafka, you get the ordering guarantee within the Kafka topic and the partition itself, not across the partitions in the topic. That means when you write a data in a Kafka topic partition, your consumer will read the data from the same partition in exactly same order. That being said, can you actually get a global ordering guarantee in Kafka? Well, we can, but we should not try to get that, because that means you are limiting the number of partitions per topic to exactly one, and that will impact your throughput. However, what you should do is you should use your partition keys, because that would ensure all the data in the same partition key will end up in the same partition in the same order. However, you should be careful about choosing the partition keys, because there could be fields you should actually choose fields with higher cardinality for your partition keys. Otherwise, you would have probably a data skew. Next, look into schema management. John has already talked about how BBC is using glue schema registry with JSON schema for improving the data quality of the application. Well, let's understand what a schema, how a schema helps, and why it is important in terms of a streaming system. A schema refers to as the structure of the data in the message. It forms a contract between your producer application and the consumer application, allowing the consumer application to interpret the data correctly written by the producer application. Now, as you are going to build a streaming data pipeline, you may end up having multiple different topics or Kinesis data stream, and each one having their own schema. Now, effectively, it means you will end up having multiple schemas. It is important to manage those schemas. And Glue Schema Registry can help here, as it can allow you to centrally discover, control, and evolve schemas, improving the data governance and data quality of your streaming application. Glue Schema Registry can also prevent downstream failures by ensuring that your producer application conforms to the schemas before writing the data to a messaging system like Kafka, so that consumer doesn't get any unexpected data. It also supports schema evolution in a compatible manner and supports the versioning of schemas. Finally, Glue Schema Registry is serverless and free to use. It supports JSON with JSON schema, Avro, and protobuf format. Next, we look into stateless versus stateful processing. While building a stream processing application, you may have a requirement of where you could use a stateless processing, or you could use something like a stateful processing, or a combination of both, depending on which part of the application we are looking at. In a stateless processing, you do not need to retain the previous state to calculate the current result. For example, you're making a date transformation from a Unix timestamp to ISO format. And BBC's use of MSK Connect to send data to S3 is a classic example of how a stateless processing looked like for this case. Whereas in a stateful processing, you need to retain the previous state in order to calculate the current result. Use cases like stream-to-stream join or data enrichment, it actually benefit from these patterns. And stream processing systems like Apache Spark and Apache Flink can be used to build a stateful processing application. Well, talking about data enrichment, it is one of the most common things that we observe across any data pipeline. You have to do some sort of enrichment of data that is coming through. While working with BBC, we found there are program events, programs like iPlayer programs that you see, and these are like event IDs that get it in this part of a stream, and it had to be enriched with the metadata. Metadata like, for example, a title, description, and many other information required. So on the fly, each event ID has to be enriched and then sent it to the downstream systems. Let's look at two of the most common data enrichment patterns that you could leverage. Let's say you have a stream processing application, and in order to actually use the stream processing application, you have to make a call from your stream processing application to an external database. And for every event, you have to make this call. Assume you're making a synchronous call. So for event A, you're making a call to the external database. After some time, you'll get back the response. Because it's synchronous, it will take some time to get you back the response. And you have to wait for the next event to be fired. And then for the next event, you make a request. After some time, you get a response back, and so on. Now, in this scenario, as it's a synchronous call, it actually increases the latency and also reduces your throughput. However, what you could do is, we could actually make an asynchronous call to the database. That means we make a call to the external database, and we do not wait for the response. We make another call to the database for the next event, and so do for the event C and D. After some time, we get the response back from the database. Now, in this scenario, as it is an asynchronous call, this actually improves the throughput and also reduces latency because there is no wait involved in the process. Stream processing system like Apache Flink supports this asynchronous API natively. There is another pattern that how you could enrich your stream processing events by getting data from some reference data from external database. Let's say you have a streaming source, Kafka, you have some IoT events, and there is a Flink job that is running to enrich those events. To enrich the events, you need the reference data, and the reference data is in another database, like a MySQL database. And then you can actually do a change data capture of all the reference data changes by using either AWS Database Migration Service or using open source Debezium on Kafka Connect. And then write those events into a secondary topic as the reference change events. Your Flink job can actually read from the second topic, the reference change events, and can store it in the Flink state. It can cache it. Now, Flink state is actually local to where the processing is happening. So the next time when it needs to enrich the event, it does not need to make a network call to the database. Rather, it would be able to get the reference data from the Flink state and enrich the event. And after the event is enriched, you send the data to the sink. With that, I come closer to the talk. This is not a holistic list that you should consider. This is some of the things that you should consider and some of the important ones. There are a couple of other things. For example, you could think about that what could be a business strategy while choosing certain services, open source versus proprietary, and so on. Now let's kind of revise what we have learned. We learned why real-time analytics is important and how AWS streaming services can help. We learned about the BBC's use case and the lessons learned throughout the journey. Finally, we looked into some of the key factors to consider while building your streaming data pipeline. Now it's your time to get started, and we are very happy to help you to get to succeed in this journey. We can provide prescriptive guidance and on-demand resources. One of them is in the QR code. So if you just scan the QR code, it will land you up into the portal, which contains all the information about the streaming services and how to get started. You could leverage the AWS streaming data partners to help you build your streaming data pipeline and realize your business benefits. And finally, it's always important to upskill yourself. So that's why you could look into some of the training content in the training and certification portal and also in the Skill Builder website. With that, I come to the end. Thank you very much. Hope you all enjoyed the session.